Hello, my name is Yung Wicket. My student ID is 1059655531. Today, I will demonstrate my IoT practical assignment project. The title of my project is Smart Farm Intrusion Detection and Pest Deterrent System using Arduino Uno and Virtual Raspberry Pi. This project is designed to simulate a smart farm security system. The main purpose is to detect possible farm intrusion, such as animals, pests, or humans entering the crop area. When the system detects a possible intruder, it will activate the warning device, including the LED, buzzer, and servo motor. In this project, Arduino Uno is used as a physical layer, while the virtual Raspberry Pi is used as the edge device. The system also includes a database, simple analytic, and web dashboard. This is the model I built for the smart farm system. The crop areas represent a protected farm zone. The sensors are installed near the entrance and the port areas so they can monitor the environment around the farm. I'm using 4 sensors. The first one is the PIR motion sensor. It is a digital sensor and it detects movement. In this demo, I will use a small door to simulate a person or animals entering the farm area. The second one is the ultrasonic sensor. It measures the distance between the sensors and an object. If the object is closer than the tree house, the system treats it as a possible intrusion. The third one is the LDR light sensor. It is an analog sensor and it detects the surrounding light level. It helps the system identify low light conditions. The fourth is the sound sensor. It is also an analog sensor. It detects abnormal sound level such as animal noise, footstep, or movement sound. For actuator, I am using 3 devices. The LED light is used as a warning light. The buzzer is used as an audible alarm. The servo motor is used to simulate a moving deterrence device, such as a small scarecrow movement. The Arduino Uno used to collect all sensor data, and the Raspberry Pi receive the data, store it into database, calculate the risk score, and send a command back to Arduino. The system flow starts from the sensor detect the farm environment, such as motions, distance, light level, and sound level. Then Arduino Uno collect the sensor readings and send them to the virtual Raspberry Pi through serial communications. The data sent from Arduino to Raspberry Pi is used this format. The means is the PIR detect motions. LDR value is 482. The distance is 999 cm, and the sound value is 46. After receiving the data, the Raspberry Pi stores the reading into MariaDB database and performs simple analytics to calculate the risk score. Then the Raspberry Pi sends either alarm on or alarm off back to Arduino. If Arduino receives alarm on, the LED turn on, the buzzer sound, and the servo motor move. If Arduino receives alarm off, all actuators are stay off. Now I will explain the simple analytic model. The system uses a rules-based risk score model. The thresholds I set are distant thresholds equals to 30 cm, LDR thresholds is 500, sound thresholds is 15. The risk score increase based on sensor conditions. If the PIR sensor detect motions, the risk score increased by 14. If the distance is less than 30 cm, the risk score is increased by 30 points. If the LDR value is less than 500, it means low light conditions, so the risk score increased by 10 points. If the sound values is greater than 15, the risk score is increased by 20 points. So the maximum risk score is 100. Then the risk level is classified like this. The 0 to 39 is equal to low, the 40 to 69 is medium, 17 and above is high. In my system, the alarm will turn on when the risk score is reached 17 or above, which means the status is high. For example, if only PIR detect motions, the score is 14, that is medium, so the alarm does not turn on yet. But if PIR detect motions and the ultrasonic sensor detect the object is closer than the 3 cm, the score becomes 17. Then the status becomes high and the Raspberry Pi sends alarm on to Arduino. This design helps reduce false alarms because the system does not depend on only one sensor. Now I will show the database before running the demo. Now the table is empty, and this means there is no sensor data stored yet. Later, when I start the system, the Raspberry Pi will automatically insert the new record into this table. I can also show the setting table. This table stores the current tree hosts such as distant tree hosts, LDR tree hosts, sound tree hosts, alarm enable, and manual mode is off. Now I start the Python A servers on the virtual Raspberry Pi. In the terminal, I run the Python 3 series reader Python. This program reads sensor data from Arduino through serial communications, calculate the risk score, store the data into the database, and send alarm on or alarm off back to Arduino. Next, I start the flag dashboard, run the python 3 apps.py, and then I open the dashboard in the browser. I refresh. This dashboard shows the latest sensor values, risk score, intrusion status, and command send, and recent database log. Now I will demonstrate the hard way. First is the normal conditions. There is no object near the sensors, no strong motions, and risk score is low. The command send is alarm off, so LED buzzer and servo motor remain off. Now I will use this door to simulate an intruder entering the farm areas. When I move the door near the entrance, the PIR sensor detect motions. This adds 40 points to the risk score. Then I move the door closer the ultrasonic sensor. Since the distance now is less than 3 cm, the system add another 30 points. Now the total risk is become 17. So the system status become high. At this point, the Raspberry Pi send alarm arms to Arduino. After Arduino received the commands, the actuator turned on. So now the buzzer is sounding, the LED is lighting up, the servo motor is moving. This simulate a pest deterrence actions. I can also make sound near the red sound sensor. If the sound is value greater than 15, the risk score increased by another 20 points. If I cover the LDR sensor and the LDR value is below 500, the risk score increased by another 10 points. This shows that the system can combine multiple sensor input to detect possible intrusion. And when the door is removed and the risk becomes lower, the Raspberry Pi send alarm off and the Arduino turn off the buzzer and LED while the servo motor return to normal position. Now I will show that the data has been saved into the database. I go back to the MariaDB and run this command. Now the table is no longer empty. The database stores each sensor reading and system result, including PIR status, LDR value, distance CMs, sound value, risk score, intrusion status, command send, buzzer status, LD status, servo status. Each row represents one reading from the Arduino. For example, if the record show risk score equal to 70, intrusion status equal to high, and command send equal to alarm on, it means the system detected high risk and activate the actuator. This proves the Raspberry Pi is successful receive data, process it, and restore it into the database. Now I will show the web dashboard. The dashboard displays the latest reading from the database, which including PIR, LDR, distance, sound, risk score, intrusion status, and command send. It also shows the sensor log over here. And the dashboard also includes the tree-hole setting. The user can change the distance tree-holes, LDR tree-holes, and the sound tree-holes. If I want the system to be more sensitive, I can increase the distance tree-holes or lower the sound tree-holes. The dashboard also has manual control button, auto mode, manual alarm on, or manual alarm off. If I click the manual alarm on, the system will force the alarm turn on. If I click the manual alarm off, the system will turn off the alarm. If I click the auto mode, the system will follow the risk score rules again. The website is useful because it allows users to monitor the farm system and control alarm from a simple interface. Now I will briefly show the important code part. First is the line 121. This line reads data from the Arduino Uno through serial communication. After that is the line 159. This line is send the command back to Arduino. So this show two-way serial communication. Next is the analytic function. We start from the line 56. For here is this part is calculate the read score, and the next is the decided the status. We start from the line 71 to line 76. After that, next part is decided the command, which is alarm on or alarm off at the line 146 to 154. And then finally, this part is insert the data into the database, which start from the line 91 and the line 100 db.commit. This saves the sensor readings, risk score, status, command, and the actuator status into MariaDB. In conclusion, this project demonstrates a complete IoT system. It includes Arduino Uno, virtual Raspberry Pi, ultrasonic sensor, LDR sensor, PIR sensor, sound sensor, LED buzzer, servo motor, MariaDB database, simple analytic, and flash dashboard. The Arduino Uno collects sensor data and send it to Raspberry Pi. Then Raspberry Pi calculate the risk score, save the data into the database, and send command back to Arduino. When the risk score reaches 70 or above, the system will send alarm on and the LED buzzer and servo motor activate. That's all is my demonstration. Thank you.